Electric motors are one of the most important inventions of the modern age. They're used in just about everything, from motor vehicles to home appliances. But to fully understand how these motors work, how they convert electrical energy into mechanical energy, one must understand magnetic fields and the magnetic force. So, what is a magnetic field? Well, generally defined, a magnetic field is a region around a magnetic object or a moving electrical charge within which the force of magnetism acts. For the purposes of our definition regarding electric motors, we'll look at the main cause, which is the movement of charge. Now, charge can move in two ways. It can be as point charges, simply moving through an open space, or through current carrying wires. Now, this is a rather simple definition of magnetic field. So, how is it more precisely defined? Well, to precisely define a magnetic field, the first thing we have to do is pick some point of interest. Find where it is that we want to define the magnetic field. Label this point of interest. Okay, the next thing we do is we take many test charges of some known charge Q and fire them through this point of interest from various angles and at various velocities. Once we did this, there's a few key things that we would find. The first thing we would find is that when the particle's velocity is along a particular axis through the point of interest, the magnetic force labeled F sub B is equal to 0. This axis, the location at which this happens, is called the zero force axis. The second thing we would find is that for all other directions of the velocity v, the magnitude of this magnetic force, F sub b, is directly proportional to v sine theta, where theta is the angle between the zero force axis and the velocity vector v. And the last thing we'd find is that the direction of the magnetic force is always perpendicular to the direction of the velocity vector v. Now, with these facts in mind, what we can essentially do is create an equation for this magnetic field strength called B. The magnetic field strength can be written as the force of magnetism divided by the magnitude of charge times the velocity of the particle. This magnetic field is measured in Tesla, the force is measured in newtons, the charge in coulombs, and the velocity in meters per second. Now, because we're concerned about electric motors, we're concerned about motion. Because we're more concerned with motion, we're more concerned with magnetic force rather than magnetic field. So to find the magnetic force, we can essentially manipulate the equation that we had just derived for magnetic field. And we'll find that the magnetic force is equal to the charge of the particle multiplied by the cross product of the velocity and field vectors. To eliminate this cross product, we can simply rewrite this equation as q v b multiplied by sine theta, where theta is the angle between these two vectors. From this equation, there are a couple of key observations that we can make about the magnetic field, or force, sorry. The first is that the magnetic force on a stationary charge is equal to 0. The second is that when the magnetic force on a charge moving parallel or anti-parallel to the field is equal to 0, and that because the magnetic force is dependent on the quantity of charge, only charged objects have some F sub b.
However, there is one key factor of the magnetic force that still needs some explanation. Where does it point? A key component of any force is where it points with respect to the object that it is acting on. This influences the motion of the object, whether it be linear or rotational. To determine where the magnetic force points, we can use something called the right-hand rule. Your middle finger represents the direction of the magnetic field, and your index finger represents the direction of the particle's velocity. When holding your hand in this configuration, your thumb points in the direction of the magnetic force. Okay, so now we're going to look at an example of the right hand rule in action. If you look on the left side of your screen, there's a diagram that represents a magnetic field and a particle moving through it. Magnetic fields can be denoted if they're pointing in or out based on whether or not there's a plus sign or a point. Think about it like an arrow. If it's coming towards you, you'll only see the tip of the arrow, whereas if you're going away, you'll see the cross of the arrow's feathers. As you can see, the magnetic field is pointing into the board. So this would be represented by your middle finger pointing into the board. Additionally, the velocity is pointing to the left, and as we said, that means that the magnetic force would be pointing up when you hold your hand in this orientation. If the magnetic field were pointing out of the board, we would have to rotate our hand 180 degrees, and now the magnetic force would be pointing downwards. Similarly, if the velocity was in the opposite direction, it would be like this, which is the same as it was initially, and then if the field is going out, but the velocity is going to the right, the field force is now pointing down. Now that we know about the magnetic force and how it relates to charged particles, let's talk about the motion of the particle. When a particle moves parallel to the field, it experiences no force, because the angle is 0. No force means no deviation from a straight line path, therefore the particle travels in a straight line. When a particle moves perpendicular to the field, the magnetic force acts perpendicular to the velocity. This is representative of a centripetal motion scenario, as the force is tangential to velocity. Therefore, the particle travels in uniform circular motion. For any particle moving between 0 and 90 degrees, the resulting motion will be both linear and circular. This creates a helical motion, which looks like a corkscrew.
Alright, now let's see how these concepts apply to electric motors. So here's the setup of the motor. A magnetic field is created by two large magnets on either side of the motor. Now, there's an armature in the center made of multiple pieces. This is the part that actually rotates. Next to the armature on either side is a connection to the battery with a brush. Now, the wire connects to one side of the armature and to the other and goes through the magnetic field produced by the magnets. So how does it actually spin? Current will flow through the wire inside of the magnetic field. This flow of current gives the negative charge of velocity. So using the right-hand rule, we can determine the magnetic force applied to the wire. This force will apply perpendicular to the direction of the current. So it either pushes the wire directly up or directly down. So what about when the wire turns over? In order to change the magnetic force on each wire so it produces circular motion, the direction of current relative to the magnetic field must remain the same. In order to produce this, the armature is split into multiple parts that touch the brush at different points as it spins. If the direction of current wasn't changed, the motor would act like a seesaw that balanced perpendicular to the ground, as the direction of the magnetic force never changed.